What went wrong? May 2012. Well, the examiner's report. Should that be an apostrophe S? This is time zone 2. You get it? And that's time zone 1. You know what? Let me crunch that for you and try and help you out here. So some people think, well, these will be the questions they'll ask again next year, these things that people kept getting wrong. And some people think these are the last things they'll ever ask again. I'm not really sure myself. Here's the list. You can pause it to take a look. I'm going to go through one by one really quite quickly. First of all, calculating rates from tangents to a curve. Let me draw out my reactance versus time graph there. Tangents, well, they're going to form a normal or 90 degrees to the curve. The IB is not going to measure it, but that's what you're trying to do. Let's take 20 seconds time. Now draw a straight line that just touches the curve at 20 seconds. Ideally, if you can stretch it to some nice numbers as well, that'll make it good. Yeah, I've got 0.5 and about 35. Checking for the normal. Yep, it's at 90 degrees to the curve. The IB specifically hates the rise over run phrase, but to be honest, it is. We'll look at the change of reactance. That goes from 0.5, 0.1, okay, it's 0.4, and trying to read off the difference in time, that's, let's say, 6 to 35. All right then. So rise over run is the change of reactance over the change of time, which is going to give me that. Who knows what the sig figs are going to be on this graph? So I'm just going to give it, let's say, 2 decimal places. Don't forget the units or you lose a point. Next up, converting meters cubed to centimeters cubed. Well, to be honest, I'm not really sure what sort of gas equation they're using with meters cubed. But if you think about a cubic meter, it's 100 centimeters on one side of the cube. Well, that's a meter. And since it's a cube, also vertically it's going to be 100 centimeters. And going into the distance there, it's going to be 100 centimeters. So a cubic meter is going to be 100 times 100 times 100 centimeters cubed. There's the conversion. Let's cube both of those. Yep, so that's 1 with 6 zeros after it, centimeters cubed. That's a meters cubed, a meter cubed. That's a million. No idea why they want you to do that. Alright, silicon dioxide, well, it's the same as diamonds, lots of tetrahedrons. Normally if you just say the word tetrahedron, that'll be good enough. You won't have to draw the diagram. I can't remember them ever asking that. But if you do have to draw it, pop oxygens in between each of those silicon atoms, and that will give you silicon dioxide. That's the definition of definition. Wow, that just blew my own mind there. And those are the definitions from the syllabus, and at the bottom you can see 3 cheeky ones that sometimes come up that aren't in the syllabus. Now, some conspiracy theorists think they've found secret messages in my video, but this isn't a secret pro-gay marriage cartoon that I found here. I am for gay marriage, not that you need to care or know. Carbon-14 with carbon-14 on a carbon date. Maybe if there were isotopes, that would be some sort of heterosexual promotion. You know what? I don't even know what I'm talking about. Carbon-14 dating is used to see how old something is if it contains carbon. Don't forget, you also need to know about iodine and cobalt isotopes as well. Volatility is how easy it is for a substance to turn into a gas, and solubility is how well it dissolves. So volatility, that's linked if it has weak intermolecular forces or very few intermolecular forces. They're not really going to be held together that much. So it's going to be quite volatile. It's going to want to become a gas more easily, or maybe it's a gas already. The classic example are these 3 organic chemicals. You have to draw the hydrogens in, of course. These are isomers. I'll rather clumsily draw in the shape. That one's like a sausage, sticky sausage if you use my terminology. And that one at the bottom right, non-sticky balls. Sticky sausage, non-sticky balls, that's how you can remember it. This is van der Waals bonding, the weakest sort of bonding. So you can see the sticky sausage ones have lots of surface area close together, lots of van der Waals bonds in orange. But the more spherical ones, there's less surface area, less van der Waals. So the sticky sausage one is the least volatile. Looking down group 7, we have the halogens there. They're all diatomic. And you can see the state symbols there. Fluorine's the most volatile. Iodine, the least volatile. Well, we're still on van der Waals, the weakest sort of intermolecular force. Iodine, more electrons, more intermolecular forces, more bonds, it's less volatile. There we go. So the most volatile would be fluorine. Most easy to gasify. And it's already a gas. That's pretty easy. Shuffling along, another question I like to ask, the isomers of C2H6O. Well, that's ethanol on the left. That has hydrogen bond capability there. And the other chemical, that just has a dipole. So hydrogen bonds, stronger bonds, going to be less volatile. The other one, more volatile. To recap, van der Waals is the weakest intermolecular force, hydrogen bonds the strongest. If you've got weak forces holding your atoms or molecules together, it's going to more likely be a gas or a liquid, and conversely, hydrogen bonds more likely to be a liquid or solid. Looking at solubility, like dissolves like. That just seems such a meaningless term, but it really means that polar molecules dissolve polar molecules, and non-polar molecules will dissolve non-polar molecules. Well, how do you know if they're polar? Well, the bond polarities and the geometry of the molecules will tell you if a molecule's polar. The classic example is to do with methane with fluorines attached. It's all tetrahedral, and the little yellow dots represent fluorine atoms. Alrighty, so methane on the far left. That's non-polar. And to know that, you'd have to look at the electronegativity difference. Carbon and hydrogen, essentially it's about the same, very, very small dipole, but fluorine loves electrons the most, it's going to be a big dipole. So methane is non-polar. When you fart in the bath, it doesn't dissolve. It doesn't dissolve in the polar water in your bath. Drawing in little dipoles there, you can see that they all cancel. The bond dipoles cancel out. Therefore, there's no molecular dipole. But those fluorine loves electrons. It's going to drag the electrons to one side of the molecule. One fluorine, two fluorines, that's going to produce a polar molecule. Three fluorines, again, the electrons are going to be dragged to one side. Overall, there's the moment of the dipole, but tetrafluoromethane, that's non-polar. All the dipoles cancel out. So the two chemicals at the end will dissolve in each other, and the three in the middle will dissolve in each other. I don't even bother to teach the equation for percentage yield. Just think about it. You expected to make 40 grams, but actually you only made 30 grams. Well, that's a 75% yield. Just keep that kind of idea in your head, and 25% error. Don't learn the equations. But the theoretical yield is the one you get from the kind of calculation table. And what you actually made, well, that's the experimental yield, if you like those calculations. Structure of graphite, well, it's made up of hexagonal layers of carbon. Those carbons, I'll draw those in there, they had 3 bonds. Well, that's strange. I thought carbon had 4 bonds. Well, graphite's arranged in layers, and that extra bond is actually delocalized electrons in between the layers that I've drawn in by the little dots there. They're delocalized so they can move around, and that allows the passage of electricity. And it also means the planes of the hexagonal sheets will slip over each other easily. That's what the IB says about how to draw a Lewis diagram, which is strange because that's in their answer scheme. Many of the questions and answers don't follow the IB way. That semicolon looks a bit confusing, but you can't have dots and lines. You said that in the syllabus. I don't think they really care. The main complaint is people just don't put the dots in when they need to. Alkanes have low reactivity. That's true. 2 reasons for that. The first reason is that the bonds in alkanes are really quite strong. So you need a lot of energy to break them to get the reaction going. So that's why they have low reactivity. Strong bonds. The second reason is that the molecule is almost always, always is non-polar. So any negative reactant, there's nothing positive to attract it. And any positive reactant, there's no part of the molecule that's a little bit negative to attract it. So that results in low reactivity. Half equations, well, let me just give you the classic one. Write out the oxidation numbers underneath. Elements are 0. Now you might notice that some don't change. SO4, the sulfate ion, doesn't change, so that you don't need to talk about that in a redox equation, really. It doesn't undergo redox. Let's look at reduction. What oxidation number's gone down? Well, copper 2+ has turned to copper. Reduction is gain of electrons. Make sure you add a couple of electrons. And oxidation is loss of electrons. The oxidation number's gone up. Make sure you've lost a couple of electrons. This was an easy one, but the electrons that you lose, they should be the same as the ones that you gain. Should be, in this case, it's 2 and 2, and that's fine. If it wasn't, you'd have to double or triple the equation, or whatever you'd have to do to make it balance. Precision and uncertainty. Wow, that is a bad picture. How old's that guy? Let's take a guess. Oh, so generous. Well, those guesses are really close to each other, and that's precise. Your guesses are close to each other, not guesses, your data points in your experiment. Now, if it was accurate, they'd be close to the real number, which is Uncertainty, well, that's equipment related, and it depends if you've got a digital or an analog instrument. Those are the two different ways to measure the uncertainty, and again, it's equipment or instrument based. Oh man, this is a huge subject. Bond angles in VSEPR theory. Well, it's all to do with charge centers and height as well. You've got two charge centers. The furthest they can get away from each other is a straight line. Three charge centers, the furthest they can get away from each other is in a triangle, equilateral triangle, almost always. Four charge centers, well, you need to go 3D there. You're going to have some sort of tetrahedral arrangement. Now, what's hating each other is the electron pairs in the valence shell. For example, carbon dioxide is linear. Boron trihydride, well, that's got three charge centers. That's going to be trigonal planar. Methane has four charge centers. Four things that want to get away from each other, so that's going to adopt a tetrahedron. Ammonia, again, four charge centers, but that top lone pair is extra repulsive, and it's going to push the electrons in the bonds down a little bit. Oh, that guy is repulsive. And for water, four charge centers, but two extra repulsive pairs of electrons. What's a charge center? I hear you cry. Single, double, triple bond, or a lone pair. Molecular polarity, see solubility, we just did it. Intermolecular forces in general. Woo! Okay, let's start with the strongest one, which is hydrogen bonds. So water is a polar molecule, and if hydrogen's attached to oxygen, fluorine, or nitrogen, you're going to have a hydrogen bond. Don't be fooled into thinking it's intra, it's inter, between the molecules. That's the strongest intermolecular force. This is the next, which is slightly weaker, just a regular dipole. And the weakest intermolecular force you need to know is instantaneous, and it's the van der Waals bond. Just lasts for a fraction of a second. Instantaneous, and it's the weakest. For changes, oh, you don't need to know POH if you're doing SL, sorry, ignore that POH. Look away now. Alrighty, so it's really quite straightforward. The concentration of the acid, it's going to be something easy like 10 to the minus 3, and that pH is the 3. That 10 to the minus 3 gives you the 3. Changes, okay, it's 10 to the minus 5 goes to 10 to the minus 8, so that's changed by a factor of 1,000. It's a logarithmic scale. Don't get confused with 1,000 times more or 1,000 times less. You've got to get that right. And you see there's a relationship. There's a difference of 3, 10 to the 3. I'm sure your teacher gave you a worksheet where this was all clear. Average bond enthalpy. How do you define it without using the word average? Mean? That's not what they want. It's the energy released by making a bond, taken over a range of values or a range of bonds. You have to say a range of bonds, a range of appropriate bonds, probably. Here's the dumb thing they asked. A few years ago, the IB asked about average bond enthalpy for this molecule here, HF. Well, there's no range. It's just one way that hydrogen can bond to fluorine.